This is my constant velocity lab for Physics 1. So what is the purpose of this lab? This lab's purpose is to observe an object's motion moving with constant velocity and compare real world versus ideal scenarios. So these observations were done using a predicted and observed model. The predicted model was generated using GlowScript code to depict the object's motion through time, whereas the tracker was used to generate observed data tracking the motion of the object at different times throughout the video. So the fundamental principles that this lab is based on are Newton's first law and Newton's second law. Newton's first law states an object in motion will remain in motion unless acted upon by another force, whereas Newton's second law states that acceleration of an object is dependent on the net force and the mass of an object. In this case, at constant velocity, the acceleration of the object is equal to zero, therefore the net force acting on the object is also equal to zero. So here's my experiment in the tracker. For the experiment, we set up a cart on the lab bench and we set up a meter stick behind it for reference. And we pushed the cart across the bench and tried to give it a constant velocity. So when importing into tracker, we used the tracker to manually input data points modeling the motion of the cart across the table. And this output a position versus time graph, which we will use later in the experiment. So the systems and surroundings of the cart. So the system is the cart itself, and the surrounding is the table and the earth. So in this force diagram, you can see that there's a normal force and there's a gravity force acting on the cart. So because the cart is moving horizontally, the gravitational pull of the earth is canceled out by the normal force exerted by the table on the cart. So some assumptions for this model are that net force is equal to zero, acceleration is equal to zero, and then the initial velocity, which is equal to the final velocity, which is equal to the average velocity. So with these assumptions, the motion is at true constant velocity, as the acceleration is zero, and as a result, the net force is also equal to zero, according to Newton's second law. So here's my code that I used for the predicted model. So I set the mass of the cart equal to 0.5 kilograms, which is approximately what the cart weighs. And then the position vector, I updated it to start at 0.002. This is to model the actual movement of the cart as the cart started a little bit displaced in the beginning of the motion. And then I set my delta t equal to 0.016 according to some calculations based on the initial velocity calculated in the observed model. And then additionally, we calculated the initial velocity and then added that to the vector of position for the ball. And this will output our predicted model. So here are my results and reasonings. When comparing the two models, it is seen that the tracker is relatively accurate in determining the change in position of the object over time, as the data set is reasonably similar to the ideal computational model. So this shows an application of Newton's second law. Since the object had a constant velocity, there must have been no net force acting on the object throughout its movement. This can be shown in the formula shown below. F net is equal to m versus the change in velocity. Since the change of velocity is zero, as the velocity is constant, then the net force is also equal to zero. So some possible sources of error that could have been introduced are the friction between the cart and the desk, improper tracking using the tracker when manually setting the data points. Some data points could have been skewed, and then the camera angle / movement of the camera while recording could also have played a factor. So what if the positive x and negative x directions were interchanged on the axes? If the axes were flipped from positive x to negative x, then the object would travel in the negative x direction, but would ultimately have the same magnitude of velocity. In this case, the object would begin at the origin and travel in the negative x direction, resulting in a negative velocity, which is still constant. So what does this mean? Is it possible to say how many pushes and pulls are added together to give the net force? Well, based on the available information, it is impossible to determine the total pushes and pulls. This is because there are several forces that were assumed to be negligible, including friction. As seen in the observed model, the object marginally accelerated and decelerated, meaning that the force is not exactly zero. So what are some conclusions we can pull? Constant velocity is linear in a position versus time graph. This is in the ideal scenario. Additionally, constant velocity motion is hard to model in real-life situations, as there are always forces such as friction and air resistance, which may result in a non-zero F net, or based on Newton's second law, in other words, a non-constant velocity, as F is equal to mass times the change in velocity.